Okay, so I'm going to talk about a paper I recently posted with Seth Lloyd. But first let me say, by way of a prelude, I don't like firewalls. I don't like information loss. I really like effective field theory. Now, these are hard times. They try our souls. Now, I do like the idea of constructing space-time geometry from entanglement, and I kind of like the spirit of ER equals EPR, although clearly there are a lot of still unanswered questions about that. And in fact, that's a matter of public record. I wrote an enthusiastic blog post not long after Juan and Lenny's paper appeared. And while I'm engaged in shameless promotion of my efforts at public outreach, so quantumfrontiers.com, that's our blog, and about 2 hours ago we posted the latest in a series of videos explaining quantum mechanics. And so if you want to take a break later, it's a 6-minute video which we created with Jorge Cham, who writes PhD comics. And so I hope you'll think it's fun. Now, I should also tell you I'm on Twitter. Maybe I should have warned you about this before. And so you can follow me. My handle is @Preskill. And so this week, I've been covering this meeting on Twitter. So whenever anything of interest, which often happens, occurs, which I think will be of interest to my loyal followers, I've tweeted it, usually if I have room, with the hashtag FuzzerFire. And so anyone who wants to add to the FuzzerFire team who's on Twitter should do so. So actually, I started my first tweet from here was during the organizational session on Monday morning. I actually find Joe very quotable. And at that time, he said something that I quoted verbatim: "Nobody has the slightest idea what is going on." And I appreciated that. And I think it made me feel less trepidation about giving this talk. And it was a good way to start things off. Actually, I quoted Joe again later that day when he said, "We all know there is not really a firewall." Probably I should have asked you what you meant by that, but it seems something that should be spread more widely.
The answer wouldn't fit in 140 characters.
Well, I found that to be a serious limitation. But okay. And while I'm doing public service announcements, I also wanted to point out that there will be a winter school, the 31st Jerusalem Winter School in Theoretical Physics, December 30th to January 9th. The school has a long and distinguished history. David Gross has been the general director for some years. But this year, for the first time, the topic will be quantum information. The title of the school is Frontiers in Quantum Information Science. And so what we're trying to do is to attract a fairly diverse audience of people who are interested in the topic. This is not for beginning graduate students. It's for postdocs and advanced students who are already seriously engaged in research. And we will cover some of the core topics of quantum information, like algorithms and complexity and quantum error correction, but also some of the ways in which quantum information is connecting with other areas of science, which we've heard about here. There will be, Rob will give lectures on entanglement and quantum field theory. Daniel will give a lecture series on quantum information and black holes. And there will also be a lecture on tensor network methods and their applications to condensed matter. And Scott will give lectures on complexity and physics. So I think it's going to be exciting. And so if you are someone who's interested in attending, or if you want to point it out to your students, there's a website. You can find it by Googling 31st Jerusalem Winter School, where you have to sign up before the deadline of November 1st. I think that's going to be a lot of fun. Okay, so I don't know, am I out of time yet?
Trying to avoid making controversial statements.
Well, and another thing I tweeted, by the way, which is something else I appreciated, was when Lenny was explaining quantum error correction and writing down an encoding circuit, I surreptitiously took a photograph and tweeted that. And when Juan was explaining tensor networks, I tweeted that too, because I found it gratifying that some of those ideas from quantum information are influencing the way people think about these problems. All right, so now for the talk. But first, the talk has a little bit of a backstory. And maybe you don't care about that, but since it involves some people who are in the room, I'll tell you anyway. So when I first heard the amps argument, I was a bit dismissive. I thought this is something that can be resolved relatively straightforwardly by what we now call A equals RB, an identification of behind the horizon with the early radiation. But when I read their paper, I started to appreciate that it's a deeper issue than I had thought at first. And so I talked to Alexei Kitaev because I knew that Alexei was a fan of a paper from 10 years ago by Gary and Juan, in which they proposed the idea that information can get out of a black hole by post-selected quantum teleportation. And actually, I had liked that paper also, which led me to be the first with Daniel Gottesman to write a paper criticizing it. And so Alexei and I were intrigued by the possibility that in this type of post-selected quantum mechanics, we can evade limitations coming from the monogamy of entanglement and potentially reconcile the smoothness of the horizon with unitarity. And we continue to discuss that from time to time. But Alexei doesn't think he should write anything about quantum gravity until he fully understands the problem. Which I admire. So meanwhile, I was corresponding with Raphael and with Douglas on this topic, and they had a number of insightful remarks about it, some of which I'll steal in my talk. So let's see, am I done with all the preliminaries? Yeah, why did I like this paper? Of the old paper by Horowitz and Maltasena. Well, you know, we've talked a lot this week about trying to understand the interior of a black hole, what's behind the horizon. But there's been very little talk about the singularity. You know, the really interesting thing about what's behind the horizon is there's a singularity there. And what are we supposed to make of that? Okay, what's supposed to happen to stuff that goes there? And so these guys, Horowitz and Maltasena, at least they had a proposal about what's supposed to happen at the singularity. And their proposal had the feature that if what happens is what they suggested, it can help us understand how black hole evaporation can be unitary. And so you might not like their idea, maybe you like it, but if you don't think they're right about what happens at the singularity, let's hear your idea. You know, it's important to have an idea. What happens when stuff goes there? Okay? So that's part of the reason that I think this is still worth thinking about. So I should say, first of all, what the idea is that they suggested. Well, I told you the idea was that information comes out of a black hole by post-selected teleportation. So I guess I should remind you what teleportation is. So I want to consider two quantum systems, which could be far apart from one another. One's right here in Santa Barbara. The other is in New York. And I have a quantum state here, and I'd like to send it to New York. But I have available as a resource something that I prepared a long time ago, anticipating that I might someday want to send that state to this place far away. And that is entanglement shared between Santa Barbara and New York. So I'm going to draw quite a few times, I think, pictures that look like this with time going upward. Here are my three systems, A, B, and C. A is where I have a quantum state, which somebody gave me today, and I don't know what it is, but I want to send it to New York. And B and C are systems, one of which is in Santa Barbara and one of which is New York, which are entangled with one another. That entanglement was prepared a long time ago. These are, say, d-dimensional systems, and any maximally entangled state of two d-dimensional systems can be expressed as some unitary transformation acting on one side of that two-part system, acting on some standard entangled state, for which I'll use the notation capital Phi. So that just means 1 over the square root of d, the sum over a basis with d elements, an orthonormal basis I for the first system, an orthonormal basis I for the second. Well, that's our maximally entangled state. And this state is some maximally entangled state, which I can always write as I tensor V, V acting on, say, the C side on Phi. And now I'm going to perform a measurement jointly on system A and system B in a maximally entangled basis. So the measurement outcome will be that A and B are now in some maximally entangled state. And I can always say, since it's some maximally entangled state, that B and C have been projected by acting with the bra and then U tensor identity acting from the right. And so that means that this is really equivalent to having Phi here and Phi here, with the V acting up here somewhere and the U acting down here somewhere. So I can redraw the picture to look like this. And so there's kind of a vivid way of describing what's going on, which you don't have to use if you don't like to, but which has visually appealing, that we can think of the state psi as propagating forward in time from here to where the entanglement occurred, then backward in time to where the entanglement was initially prepared, and then forward in time again. And then in system C, we will now have the result of first applying U and then applying V. So VU psi C. Okay? Except the thing is that in system C, what we really have is just the reduced state of a maximally entangled state. And that's always just a garbage state. It's maximally mixed. Okay? Normally, when we make this entangled measurement, there are d squared possible outcomes, all occurring equiprobably. But once I know what the outcome is, then we can send the information about what the outcome was from Santa Barbara to New York just by calling up on the telephone. And if we also know what entangled state we prepared some time ago, then we know V and we know U, and we can apply their inverses and recover the state psi in New York. That's quantum teleportation. Okay? And it's done experimentally these days with photons and ions and superconducting circuits and so on. Now, so what, I guess I'll call them HM because they have so many syllables in their names. So what HM said was, now let's consider a similar scenario where we have a black hole. There it is. And I want to consider a matter system which falls into the black hole. So I'll label that M for matter, the collapsing matter from which the black hole formed. But at the horizon, we have an entangled state of the Hawking modes outside the horizon and the Hawking modes inside. I'll just call those out and in. And let's take a microcanonical point of view about the black hole. We think of the out states as labeling all the different possible out Hawking quanta that could be produced when a black hole evaporates, when it has a mass very close to m. Okay? And those will be paired with the quote-unquote negative energy quantum quanta behind the horizon. So I can think of this maximally entangled state as just phi if I adopt suitable bases of the in and out systems. Now, I really want to take this seriously, though. Of course, what I'm trying to describe is an unrest state where I have maximal entanglement between degrees of freedom inside and outside. That's interesting to us because it means we're talking about a state which is smooth at the horizon. So sometimes we say, well, we can think of these as the positive energy and negative energy Hawking quanta. Well, that's not quite precise for a couple of reasons. First of all, we don't really mean negative energy. The killing vector, which is time-like outside the horizon, becomes space-like inside. So we're really talking about momentum behind the horizon, not energy. But furthermore, the evaporating black hole geometry isn't really stationary. Black hole is evaporating. We don't have a precise killing vector. But I'm going to take it for granted that we can make precise the idea that there's a maximally entangled state between these two systems. And you have to take that seriously. It's important for this proposal. Now, what's happening here, when the matter arrives at the singularity, we are going to demand that there is a boundary condition imposed at the singularity, the HM boundary condition, namely that the state gets projected onto one particular maximally entangled state of the two systems, M and N. Okay? Well, that's kind of a crazy thing to say. But on the other hand, I mean, what do you want to say happens at the singularity? It's not completely crazy from the point of view that sometimes we're willing, when we consider cosmological spacetimes which have initial singularities, to say that there should be some quantum boundary condition, some wave function of the universe. And here we have a final, a future space-like singularity. And we're saying, well, why not put a boundary condition there as well and specify a particular quantum state? That was their proposal. And now, because some definite entangled state has been projected out here, which I've labeled by S, which corresponded to the U here, the labels that particular maximally entangled state, now there's no need for any classical communication from where that projection occurred to this state to get a uniquely determined quantum state, which is just the state of the infalling matter, acted upon by a unitary transformation, which is just the unitary transformation that specifies that final state boundary condition, which I called S. And so just as I implicitly suggested here, that we can think of this diagram which goes forward in time and back in time and forward in time again as being equivalent to something which has a consistent causal ordering, where we can just think of time moving in this direction. So we would like to say here that this is equivalent from the point of view of someone outside the horizon. We can straighten out the bend forward and back in time to get an equivalent description of physics outside the horizon, in which the black hole S matrix acts on the infalling matter to produce the outgoing state of the Hawking radiation. Okay? Tom?
You're allowing that last little bit of evolution to be not in there.
Which little bit of evolution?
When you get the singularity,
Well,
you're turning the evolution on.
right. So what we're doing is we are not playing by the usual rules of quantum mechanics. We are modifying quantum mechanics inside the horizon, okay? By saying that one particular unique state is allowed to occur when this entangled measurement happens. Okay, so that's what I mean when I say it's post-selected teleportation. We don't have that any possible outcome of that entanglement could occur. The boundary condition says just one. And indeed, that will change the rules in ways which might scare us a little bit, but maybe have some nice features too. Okay, so there's no problem with saying that this matrix S is some scrambling S matrix, which we usually think about when we adopt the complementarity point of view of physics outside the horizon. But there are some kind of nice things about this picture from the point of view of trying to reconcile physics outside the horizon with physics inside the horizon. So if I'll dispense with S in this picture. I really should have a stamp with this causal structure. I'm going to draw it quite a few times, I think. But so our information flow looks like this. But if we consider a sequence of nice slices through this geometry, space-like slices, then in this picture, a type of quantum cloning has occurred. Okay? The same quantum information can be decoded in its scrambled form outside the horizon and also inside the horizon. And so on the same spatial slice, we have the quantum information in two places. That's cloning. Now, normally, unitary evolution in quantum mechanics will not allow us to clone quantum states because that would violate the linearity of quantum mechanics. But in this post-selected scenario, cloning is allowed. And so it's possible to have the same quantum state at two places on the slice. You mean, why don't I say there are three places? Well, what I would say is the information that fell in, there may be, can be decoded. Well, okay. If you like, you can say three places. You're saying it goes forward, it goes back, and then it goes forward again. I would know if I were behind the horizon how to decode the infalling state on this region inside, and I would also know how to decode it here, is what I meant. Okay. Now, another feature is we can think, as we did here and as I indicated here, of straightening out the process and saying, well, it's really equivalent to something which has a consistent causal ordering. And now I can ask, well, suppose I consider operators acting in the interior of the black hole and operators acting in the exterior. Well, those operators don't commute with one another. And they don't commute with one another for a reason which, from this perspective, is readily apparent. We can really think of those operators as acting on the same system at two different quote-unquote times after we've adopted this consistent causal ordering of the information flow in the black hole spacetime. Okay? So we really have kind of a nice realization of complementarity in the form that we might like. We can really think of the interior as being a redundant description of what's in the exterior. And so we really are looking at the same system in a sense in two different ways, which from this point of view is the same system at two different times. We can also see that our usual notion of monogamy of entanglement can be relaxed in this setting. So we can imagine, now I'll put back my entangling unitary at the boundary condition and having, say, a pair of subsystems of the collapsing matter arriving at the singularity. So I'm going to draw it the way I did before. Kind of looks like that. So this is radiation that comes out at an earlier time. This comes out at a later time. But if this, say, is a product state, this unitary can entangle the two systems. And if you like, we can think of what I called out 1 and out 2 as the early radiation and the late radiation emitted from an evaporating black hole, which we think should generically be entangled with one another. But in this case, it's okay for out 1 and out 2 to be entangled with one another, but for out 1 to be also entangled with its partners in 1 and out 2 to be entangled with in 2, so that we can have a smooth horizon and unitarity, which produces entanglement between the radiation that comes out early and the radiation that comes out late. If you like, you can consider the case of feeding a black hole to maintain it for a long time before we finally let it evaporate. And that's kind of instructive to do because we can see that this S matrix that describes the final state boundary condition is not completely arbitrary. We should expect it to have certain features which will agree with what we expect from the point of view of the complementary physics outside the horizon. So specifically, if I consider sending in pulses of matter to maintain the black hole's mass for a while, and then I'll have outgoing radiation at different times, even if we maintain the black hole for a time which is long compared to its natural evaporation time, we shouldn't expect arbitrary entanglement between the early radiation and the late radiation if both systems have a dimension which is large compared to e to the s. Because from the exterior point of view, we ought not to be able to at any time have more entropy in the radiation than the maximal entropy of that counts the microstates of the black hole that the radiation interacts with, because the overall state is pure. So it should be that the entropy goes up towards the black hole entropy, stays there for a while, and eventually when we let the thing evaporate, comes down. So one way of saying that is we can think of the radiation state as being described by one of the tensor network states that Juan described, where he drew a picture like this, where these are the physical degrees of freedom, and the vertices are connected together by these bonds which represent the entanglement between the successive bonds. So if we think of the radiation in a sequence of radial shells, with each one of these vertices representing such a shell, the amount of entanglement between all the radiation outside a shell and the amount inside a shell can't be larger than the black hole entropy. So the bond dimension of this tensor network, a matrix product state, can't exceed the number of states of the black hole. Or in other words, where we cut it, this state will have an entropy which is no larger than the black hole entropy.
It also should be much smaller.
Well, it could be smaller for a while, but we would expect that if we have scrambling dynamics, that it would, after we've been feeding the black hole for a long time, that it would approach the maximal entropy by virtue of being nearly maximally entangled with the microscopic degrees of freedom. Samir. Well, no. I mean, I'm really talking about the fine-grained entropy, in the von Neumann entropy sense. So I'm trying to describe the amount of entanglement between all the radiation emitted after a certain time and all the radiation emitted before that time. Okay. Now, when I spoke about the polygamy of entanglement, that we could have out 1 and out 2 entangled with one another, but also simultaneously entangled with their partners behind the horizon, something that would not be possible in ordinary quantum mechanics, but with post-selection is possible. It's a rather delicate statement for a reason that we should note. if I go back to the picture of teleportation, I could say it this way. So I have this teleportation information flow diagram. Here's the preparation of the entanglement. Here's the projection onto an entangled state. And these are systems A, B, C. And we could think of these boxes as insertions of projectors for the purpose of verifying that entanglement. They know exactly what the entangled state is supposed to be, so phi, for example. Then, in this case, both projectors can succeed in verifying the maximal entanglement with probability 1. That's what I mean when I say the entanglement is polygamous, because once we've done the post-selection, we know that here, that particular maximally entangled state will be projected out with certainty. So that's already true when we check the entanglement here. And here we've prepared the entangled state, and we can verify that it's entangled the way we expected. So in that sense, System B, because we post-selected a particular entangled state, can be maximally entangled with both A and C. But if we imagine trying to do the verification of the entanglement in the other order, a picture like that, then, in fact, each entanglement verifying projection would succeed only with the probability 1 over d squared. Okay? So the order in which the projectors are placed is important for reaching this conclusion. And so if we're going to have to think some more about exactly what it means operationally to say that we've violated monogamy of entanglement. And in some sense, we need to somehow disallow or declare illegal these projections which act on the systems that are moving forward in time and also backward in time, if you would like to use that language. Because really what I've said here is that if I perform this projection, say, then the probability that I assign to outcomes of that measurement can depend on what measurements I will choose to do in the future. That's really a violation of causality. And that's very characteristic of post-selected quantum mechanics, that we can easily get into situations where measurements today can depend on choices that we will make in the future. And that type of causality violation is something that we would like to avoid in this type of scenario. Okay. So let's think about things that could go wrong that could make this attempt to find a consistent causal ordering for the information flow, which would give rise to a nice picture of complementarity. What are some of the ways that could fail? Well, one thing that could be a problem would be if somehow the matter would be able to interact with outgoing radiation which encodes the state of the matter. That would be sort of a manifestly acausal phenomenon. I guess we can draw it this way. So that if I have some interaction between the matter system, this is the matter coming in, and this is the outgoing radiation. So what we've allowed here is for the radiation to, in effect, send a signal back to the matter that encodes the same state. And that type of interaction, this is just some unitary interaction between the two systems, would prevent us from being able to straighten out the diagram and give it a consistent causal ordering. But on the other hand, what we would be saying, if that could occur, is that the information that was carried into the black hole by the collapsing matter came out before the matter fell behind the horizon, and so it was able to interact with itself. And so it's perfectly reasonable to say that the information doesn't come out in the radiation until after the matter falls in. And that would allow us to avoid this type of acausal process. Otherwise, signaling in the other direction would be okay. It would be all right for the matter to send signals. Well, I'm saying that this process would mean, what I was trying to draw was a information flow in which the information that is carried by the matter comes out in the radiation and interacts with the matter before it falls in. But let's take the point of view of the outside observer. So what we're saying is we send in some matter in a particular state. It gets absorbed, it gets scrambled, and then it comes out after some delay. That would be okay. That would mean this process doesn't occur. Okay? So in other words, it's something that would be bad if it could happen, but it's not something that our expectations from the point of view of the outside observer is that it won't happen. How do I prevent it from happening? Well, I'm sorry. Maybe the diagram is a little bit misleading. Of course, there are lots of quanta in the infalling matter. There are lots of quanta in the outgoing radiation. I don't mean to say that the matter won't interact with the radiation. I'm just saying it won't interact with radiation that encodes the same quantum state. Okay. And if I consider in particular, maybe this will help to clarify the answer to the question, a process in which well, that's a little bit different. I'll draw a picture like this, I guess, later on. So it's okay for the matter to send a signal that allows it to interact with the outgoing radiation if that radiation isn't carrying the same quantum information as what the matter is interacting with, because that won't prevent us from pulling this diagram straight and giving it a consistent causal order. Okay. So what else do we have to worry about? Well, the other things we have to worry about are potential entangling interactions between the systems that are behind the horizon, the infalling radiation, and the matter. Or potentially interactions between the infalling radiation and the outgoing radiation, which although we might be protected against those by the causal structure as far as direct interaction is concerned, a malicious agent could interact first with the outgoing radiation, then fall through the horizon and interact with the infalling radiation behind the horizon, potentially performing an entangling operation. So either one of those things would be bad. Another way of saying it is, we have a projection on to a maximally entangled state here. And let's think of this as the matter, infalling radiation, and outgoing radiation. An entangling interaction between the matter and the infalling radiation behind the horizon could have the effect that we're really not projecting onto a maximally entangled state. Perhaps I didn't emphasize sufficiently that if I want this teleportation process to have perfect fidelity, then both the initial state that we prepare and the state that we project out should be maximally entangled. In other words, U and V should be unitary operators. Otherwise, a state that's received at system C will be compromised. Some of its information will be lost. We won't be able to recover it by applying a physical operation to that system. So we really want these to be exactly maximally entangled. And this type of entangling interaction could have the effect that we're not really projecting onto a maximally entangled state. In fact, in the extreme case, this unitary could undo the entanglement so that we get an information flow that looks like this, in which case what comes out in the radiation would be completely uncorrelated with what fell in. Okay? And likewise, if we don't really have a maximally entangled state of the in and out system, then we're doing teleportation but with an imperfectly prepared initial entangled state, and that would also compromise the fidelity. So both of these things are dangerous. And in fact, this was the point of the criticism that Gottesman and I gave back in 2003, not long after Gary and Juan wrote their paper. We said it seems that the dynamics has to be tuned just so that that type of entangling interaction doesn't have the effect that we're projecting onto a state which is not precisely maximally entangled. And same thing here. And actually, Seth Lloyd, my co-author in this work, wrote a criticism of the criticism in which he made an observation, which is that, yes, that's true, but it almost works if you just choose a generic state at the singularity. It will very nearly be maximally entangled. And actually, this is just the pageism that Daniel was talking about earlier. In fact, I was going to write down exactly one of his equations to make this point. So let's suppose, just to maybe make the argument sharper, that we consider dividing the matter into two subsystems. Maybe we should think of subsystem 1 as the matter states from which a black hole can be made in rapid collapse, in a collapse which takes a time of order m, say, whereas most black hole microstates can only be created if we feed in the matter over a time which is of order the evaporation time. In other words, the formation will look like the evaporation process in reverse. That takes much longer, a time of order m cubed. And thinking about the creation of such black holes that we have to create over a long time in which there is simultaneously Hawking radiation being emitted, it's kind of confusing. So let's stick with the case of rapid collapse and think of M1 as the states which will collapse rapidly. And M2 as all the other degrees of freedom. But suppose we just fix the state of M2. Let's say it's in its vacuum state. So now our decomposition into subsystems really becomes a subspace of all the microstates that collapse rapidly with some fixed state for everything else. Okay? And then we can say, well, suppose maybe we have some entangling interaction that occurs between these two systems, but we also choose some typical state as our final state boundary condition. Well, we don't really want to choose a random state. The laws of physics should pick out some particular state because that's going to determine the black hole S matrix. And we don't really think the black hole S matrix is going to be Haar random because it's so hard to prepare Haar random states. It takes exponential time. It would be something, though, that's scrambling. But just as a first pass, suppose we consider our final state boundary condition to be typical of Haar measure. Okay? So what we're really doing in this case, now I'm very lucky that I had the right people preceding me at this meeting. Lenny talked about how if we want to understand whether information is destroyed or not, we should look at a system and we should entangle it with a reference system so that in effect we are considering all the possible states of that system. So let me consider entangling this subsystem of the matter M1 with a reference system N1. And I'm choosing some particular state of M2. And I also have the infalling radiation entangled with the outgoing radiation. let this just be a Haar random unitary, or unitary with respect to whatever our ensemble is, but I'll assume it's Haar, and then project onto some particular state. So that's just a way of describing a projection onto a generic state. We fix the state, and then we apply a Haar typical unitary. So really what we are doing here, since we picked out some particular direction or some particular vector in the state M2, is we have prepared a Haar random state of the composite system of N1 and the Hilbert space of the outgoing radiation. And I think Daniel wrote down this equation that if we consider integrating over the normalized invariant Haar measure and ask what is the distance of the reduced density operator when I trace out the out system of our reference system N1 from the maximally entangled state in the one norm, that will be less than or equal to a square root of the ratio of dimensions, which I can say M1, which is the same as the dimension of N1, divided by the dimension of the Hilbert space of the outgoing radiation. So that's just as Daniel said, what Don Page is always talking about. If I take a random state of a Hilbert space, which has a decomposition into two systems, one of which is bigger than the other, then the density operator will be very close to maximally mixed. And in this case, where this is a system which has an entropy which is subleading, goes like area to the 3/2, say, in the case of rapid collapse, instead of area, this is going to be as small as something like e to the minus the black hole entropy over 2, since the black hole entropy, e to the black hole entropy, is the dimension of this space. So that's really, really, really close to maximally mixed. And what it means that it's really, really, really close to maximally mixed is that the reference system is almost precisely maximally entangled with a subsystem of the outgoing radiation. And that means I can apply, never mind complexity, might be hard, as we heard, but I can apply a decoding unitary to the outgoing radiation Hilbert space, which will isolate that system, which is maximally entangled with N1, and get almost precisely a maximally entangled state with the reference system. And what that means is that if I consider some arbitrary infalling state of M1, I can decode the radiation, attaining a fidelity which is very close to 1. It's just 1 minus this this L1 distance, so entropy of the black hole over 2. So we can get an almost perfect decoding of the state if we just choose our boundary condition to be a generic unitary. And we could reach a similar conclusion if we didn't consider Haar typical, but typical in some ensemble of unitaries which are easier to realize with a smaller quantum circuit, like a 2 design, for example. So it almost works. We almost got all the information out, but it's not exact. It's not exact. Now, that's bad, right? We really want the unitarity to be exact. And so I would, I was hoping to solve this problem, that maybe there's some way of choosing our final state boundary condition so that it will be stable with respect to small deformations of the entangling dynamics, but I don't know how to do that. So I really don't know, and this is the Juan.
Would you say that this is a small non-perturbative effect that the whole space-time picture should capture?
Yeah. Well, I don't know whether to say that or not. Is that what you would say?
Yeah.
I liked it. Say it again.
Once you disclose, you
Small
close.
non-perturbative effect that violates unitary adjustment?
Small non-perturbative effect.
Oh, small non-perturbative effect of fixing. Oh.
Well, that's true. It is of the same order as the effects, that we expect to be non-perturbative in the context of black hole quantum mechanics.
Actually, I didn't realize you were doing perturbation theory.
Well, I wasn't, right. That's right. And so that's why I don't know exactly what Juan means, but I like it anyway. So somehow we've got to do better. And as far as I can tell, we really do have to tune our final state condition, and in kind of a peculiar way. And this is the baggage that the HM proposal carries. That somehow we need the dynamics behind the horizon to have the feature that maybe there will be entangling interactions between infalling radiation and the infalling matter. But those must, in some sense, get undone before the final state boundary condition is applied. So we will really get precise maximal entanglement of the projected state and precise unitarity. At least that's one way of describing how it would work.
So, sorry, can I ask a question about your language a little bit? I mean, You call that a tune, but suppose the principle is unitarity. Then it's not as though you're tuning anything just because the other choices aren't really viable.
Well, if you're happy with it.
No, I know what you're asking. It's a question about quantum gravity at the singularity.
Well, okay. So I would say
it wouldn't really be a tune because you don't have those parameters to vary, actually.
Right. So I would say there are two ways we could go. We could somehow argue that the fine-tuning is in some sense not required in the sense, well, look, okay, here's the difference between what Gottesman and I said in 2003 and what I'm saying now. So in 2003, Gottesman and I said, look, in order for this to really be unitary, it looks like you've got to tune the dynamics just so. Isn't that disgusting? And what I'm saying now with Seth is in order for this to work, for you to have exact unitarity, you've got to tune the dynamics just so. Hey, that's pretty cool. So the story has really changed. And the new story is that maybe we can learn something interesting about the dynamics behind the horizon by demanding that the scenario really preserves exact unitarity. Gary wants to say something.
Well, I don't know, but just maybe to follow up on what Juan was saying, at this very, very low probability, e to the minus s black hole, there's the possibility of not forming a black hole at all, right? Or the black hole can just sort of spontaneously evaporate and emit, all its mass instantaneously. So maybe that's the kind of non-perturbative correction one needs, a case where there isn't a singularity in the classical geometry, and that sort of thing might.
Raphael.
John, so one process that I think could disrupt this, in fact, at a level worse than the one that you've identified, is if somebody, while falling in, were to disrupt the vacuum. Measure B and A. Is that correct? And well, is your miraculous dynamics basically preventing me from performing that measurement?
The miraculous dynamics prevents you from doing bad things if the miracle really occurs, because that agent that you're describing behind the horizon is really just part of the matter system.
Yeah.
And we are demanding that the unitary dynamics of the infalling observer and the infalling radiation have the property that, the guy doesn't really, we can debate free will.
But I don't really have free will, right?
It's just unitary. Yeah. And the unitary interaction has to have a certain property, and it applies to every agent who falls in.
Good. I need to follow up on that. This was just the beginning. So I think there's a fairly precise analog between this proposal and donkey maps or A equals RB, and that both suffer from similar obstructions or difficulties. One is if you had the black hole in a state such that the zone was pure, then in and out simply wouldn't be entangled in the right way. But another, which I find in a way more physical, is this problem of the frozen vacuum. Now you might say, I think your answer now is telling me that if I tried to see that the vacuum is frozen at the horizon, I couldn't do that because I've sort of been post-selected out. I wouldn't exist. But I don't think it helps. I think the horizon is still special because I can establish that any particular Rindler horizon that I pick is not a black hole horizon by performing this experiment successfully. you see what I'm saying? So if the post-selected dynamics prevents me from doing this experiment at all for a black hole horizon, I can still determine that something is not a black hole horizon by performing that experiment. And I think that violates the equivalence principle because it tells me that I can locally exclude the possibility that a certain Rindler horizon is also a black hole horizon.
Well, I didn't exactly understand that, but I certainly would concede, and this is part of what, when we were discussing this earlier, I think made us think the idea has very serious flaws, that the measurement theory in this scenario is disturbingly bizarre. And but in this case, well, I don't know exactly what you meant. All I can say is, as far as I can tell, well, look, I understand the criticism, I guess, that Juan and Gary are making. This argument, of course, relies on a semi-classical causal structure, which we should not have such confidence in as to think that we're, doing a calculation to this kind of accuracy. And I guess is that a fair statement of your point?
No, sorry, no.
Well, I'm just, he nodded, but no, I'm sorry, I meant Gary's point.
Yes.
So,
But apart from that, I'm saying that within this semi-classical picture, that what what I'm asserting, which is probably taking the picture more seriously than it deserves to be taken, is that the dynamics has to be tuned in a certain way, and that will place limitations on any horizon crossing agent who will be subject to this post-selected condition.
But John, so quick question. So you need a very special small effect of this size? Isn't that part of the upshot of that?
Well, I'm
you just
saying
had some generic non-perturbative effect. Yeah, sure, they're this size, but you really need.
Well, that's right. But I mean, I guess the point that Juan and Gary are making is that I shouldn't necessarily, and maybe this is Eva's point too, that we don't really have a case that there's a problem when we're making an error this small because we don't trust my discussion to that kind of accuracy. And Raphael vehemently is shaking his head no. Scott.
Okay. So I have a lot of worries about post-selection scenarios, as fun as they are to think about. But one example of a worry is that if you have a post-selected final state, then it seems like you can solve NP-complete problems instantaneously by just post-selecting on the branch of the wave function where you happen to have found a solution. So I guess I'm wondering, is there any reason in your scenario why that wouldn't happen? And actually, there are two versions of the question: one for the outside observer and one for the infalling observer.
Yeah. Well, let's suppose as a model, we consider the case in which we have a post-selected state, which is exactly maximally entangling, and no interaction between the infalling radiation and the infalling matter. So in that case, I think I can say that for the purpose of describing, any of the correlations that the evolution encodes, that it really is equivalent to this straightened out process in which there is unitary evolution occurring all along, which would be subject to computational complexity limitations.
So you're saying it's not only unitary, but there's an efficient circuit for it?
Yeah, I would say that all this evolution can be described, well, actually, modulo the fact that, that's sort of an assertion that I'm making because you've drummed into me that I should not, allow the laws of physics to violate computational complexity constraints. A lot depends on exactly what this S matrix is, which picks out the maximally entangled state. So I'm taking it for granted that it is a unitary which can be efficiently constructed by a quantum circuit. And everything is subject, I think, to the usual limitations of quantum complexity.
What about for the infalling observer, though?
Well, I think for the infalling observer, again, if we take that special model, which is the easiest to talk about, the infalling observer will, experience just normal physics. Now, of course, it's really fun to ask, what does that observer who follows information backward in time think is going on. And I think if you just look at the correlators, what they say is that it's equivalent to a process in which you have Hamiltonian evolution forward in time to the singularity, backward in time to the horizon, and then forward again. But at all times, just described by some local Hamiltonian.
John, the S matrix that you talk about right here, the S matrix, I'm a little confused about what it's supposed to depend on. So if I have a black hole of mass m, is it unique given the mass? Does it depend on how I formed the black hole?
Well, it's determined by the mass, and it is just what you think it is, right? It is the unitary which describes the relationship between infalling matter and the outgoing radiation.
But I wouldn't have thought that that was unique. I would have thought that that depended on the initial state that I formed the black hole from.
Is this the laws of physics? It's a universal thing. It's the time evolution operator.
Sorry?
It's the time evolution operator. It just depends on the laws of physics.
Well, it doesn't depend on the black hole. It depends on the initial state that formed the black hole.
Yeah. I mean, in a way, the picture is a little unfair because I'm describing arbitrary, infalling states, and I'm drawing a fixed geometry or causal structure, which, of course, is the geometry is determined by the state. But I mean, what I mean, I think it's unitary in the sense that you would expect, a unitary relationship between the asymptotic infalling matter state and outgoing radiation state.
Just a comment and a question. A comment on the frozen vacuum question. I mean, one way to rephrase it, I think, would be to say that you should allow for the possibility that the inside and the outside are not exactly entangled, in particular if I create a perturbation. And in these state-dependent scenarios, I think that's not so hard to arrange. So, I mean, I think the frozen vacuum argument is possible to evade in these state-dependent scenarios. You can give a criteria for when the inside and the outside are not exactly entangled. I mean, if I perturb the outside, it shouldn't be exactly entangled. So, I mean, I think it requires some criteria here. Okay. The other thing I'm worried about, though, in this setup is about the commutator between the inside and the outside. So, you want the infalling observer to experience normal physics. But what if I have somebody, the infalling observer does a measurement, somebody outside does a measurement, and then the infalling observer repeats his previous measurement. So he ought to get the same result as he got 1 microsecond ago. But this seems to allow for the possibility that that won't happen. So I'm worried about the commutator not vanishing or not being small.
Well, I think this non-commutativity is really, the causal description of it is that the, action or operator behind the horizon can, in principle, affect the outgoing radiation. Because once I replace the process by one which is, causally ordered, then really we're talking about, in effect, operators acting at two different times. And so the earlier action can, in principle, affect what the later one sees. But on the other hand, the whole thing is just evolving unitarily. So I think we have to be a little bit, of course we do it all the time, to be a little bit careful talking about the action of sources and, how they'll affect the sources. Yeah.
So I didn't understand. Are you going to post-select this observer out, or are you going to say that if this really happens, then this physics inside is not semi-classical, right? Because it depends on what's happening very far away. So this observer might see very funny things that are happening which he can't describe within local scenarios because they are influenced by what happened very far away. So I'm worried about normal physics holding for the infalling observer.
I don't really think that's what the picture is suggesting. Now, what it is suggesting is that the observer who arrives at the singularity gets in a very unpleasant shock, because in this picture the rapidly mixing S matrix is acting in a very non-local way and in a very brutal way, very suddenly. And terrible things happen at singularities, and this is a terrible thing. But I don't see that necessarily is the case that the experience of the infalling observer will be affected by action on the outgoing radiation. Juan.
I guess it's probably necessary to combine these perhaps with these arguments about complexity, so that when you go in, you do measurements of some limited or easy, let's say, operators and so on, then you hide this whole non-causal evolution and so on. This non-causal effect is given very complex things are actually not going to do.
Well.
Yeah, I mean, it might be that for easy operators, we don't have this type of argument, but the density measure might prevent this commutator. Okay, you do.
I see.
I mean, someone measures the radiation, so your future stuff happens. But it's happening far away from your point.
It has to be feedback because typically communicated to be large in sample space. You have to be careful about it.
Well, you know, I described it as you have both systems on the same slice and they don't commute, but I think the physics can be equivalently described by saying that an action behind the horizon will have an effect on the outgoing radiation, which, you know, doesn't I mean, it's consistent with a causal description of the quote-unquote experience of the infaller who gets hit by the scrambling unitary and is pulled back to the horizon and then moves on.
Water is not making a measurement in this, a measurement in the ordinary sense of the radiation. Unitary transformation.
Right.
One should derive quantum mechanics to this guy.
Yeah. Right, that's right. So the way I would prefer to think about the measurement theory is that we just have some unitary system, and measurements arise in the way they usually do in an Everett picture. Don.
Just to make sure I'm following this, the interesting experiment we discussed here is the one that we already discussed on polling news number 3.
Yeah. Okay. So maybe.
I'm not sure. You mentioned that there was this funny thing that's happening. I'm not sure you ever proposed before resolution required.
Yeah. Okay. So now let's. Yeah, okay, that's a good idea. So now I want to consider a agent who crosses the horizon who has been assigned the task of applying some entangling unitary to the radiation outside and the infalling radiation inside. And again, continuing to take the classical causal structure seriously, the way such an operation is applied is that horizon crosser who wants to apply some operation that straddles the horizon will first interact with the radiation outside the horizon, then fall through and interact with the system inside. Okay? But now, once that observer we should really think of as just another component or subsystem of the infalling matter. So that agent who falls through the horizon will himself be subject to the final state post-selection. So if we have and this is the main, well, if we have, as I've described it, tuned dynamics so that we really get perfect unitarity because we're projecting onto a maximally entangled state, that malicious agent will not be able to spoil unitarity. What that agent does is he interacts with the outside radiation and then jumps in. And then by our assumption that we've adjusted the dynamics just right in the interior, that nothing that agent does, which is governed by that unitary dynamics behind the horizon, will be able to spoil unitarity. Yeah, let me see if I can. I'm not sure how clear that was.
I'm not sure I asked about the right diagram.
You're talking about this diagram.
Yeah, I thought that was something. Maybe I misunderstood that one. I thought that was the case where the observer was trying to first verify the external entanglement and then verify entanglement across the horizon.
Right, but so I'm going to. So there are two kinds of things to worry about. So one I've already discussed. So one is operations that can occur behind the horizon, which might be entangling between the infalling matter and the infalling radiation. And so at least if we take our calculation seriously, it looks like we have to adjust things just so to really get precise unitarity. So let's suppose we've done that. Okay. So now we're concerned about the effects of observers who apply entangling operations to the outgoing radiation and the infalling system, which is what this is supposed to represent. So we have a picture which looks kind of like this. So what this agent is going to, let's say, apply two successive unitaries, but I haven't drawn the one behind the horizon. So the first one is that agent interacts with some outgoing radiation which was produced previously. And we can think of the agent as just part of the matter system that could potentially fall in. And then that agent goes behind the horizon and now just regarded as some subsystem of possible matter states will be subject to a post-selection condition which preserves exact unitarity. So once he falls in, we can just straighten out this process and replace it by one which is causally ordered. So there's no deviation from unitarity caused by the action of that observer, because once he falls in, he is himself subject to our post-selection condition, which has been set just so as to preserve unitarity. So that is how, by inoculating ourselves against violations of unitarity caused by entangling interactions in the interior, we've also prevented the malicious agent who acts sequentially, first on the outside system and on the inside system, from foiling us.
Okay. Did you discuss anything at all about what happens if somebody measures, let's say, RB in the outside radiation, what the effect would be on the interior? In particular, what does...
Well, in this picture, there's no effect on the interior.
So you don't think it would create a particle in the interior?
Right. Because...
This is one of the few things I think we agree about. But,
right. So I think in this picture, although I said that, we have the same system. We have a redundancy in the sense that we can think of the interior and the exterior as the same system. That once we assign a consistent causal ordering to the dynamics, we should really think of the outgoing radiation as being the same system that's behind the horizon, but at a later time.
Okay. So do we have a distinctly different prediction for E, for at least what Juan and I wrote and what you would predict? Namely, that if Alice, or we may wind up just saying that Alice cannot do the experiment, but let's forget that for a minute.
Yeah.
Supposing Alice measures RB, and I'm not sure whether to think about the case where Bob falls through the horizon, or Alice herself, after having measured RB and knows the answer, whether she's the one who falls through the horizon. But you would say she detects no particle made by the process of measuring RB.
Right.
And I think we would probably, Juan, would you agree that that should make a particle behind the horizon?
Yeah, but maybe it's produced by the post-selection. So because in order to, here he describes the matter following.
Yeah.
So now RB is not part of radiation, maximum entanglement following.
Wait.
So it has to close these lines that goes down.
Yeah.
Close to go up.
So what are you saying? You're saying that this theory will create a particle behind it? That there will be a particle behind it? Good. So
Well, I don't know. It seems like a different situation to me because we have addressed the polygamy of entanglement by actually, through post-selection, allowing entanglement to be shared for system B between both the interior and the outside.
I'm confused by your answer and Juan's answer.
Well, I guess we don't seem to be agreeing.
Is that right? We're not agreeing?
Yeah.
Okay. Good. That's good. That's good.
Okay.
Yeah, so I have a simple-minded question about the post-selection. At some point you were saying that it's just the assumption that the dynamics is such that the system will end up in a particular state, which doesn't sound to me that drastic. If I take a photon and I let it excite an hydrogen atom, and the hydrogen atom gets excited, falls back to its ground state, emits a photon, then my S matrix only involves one photon coming in, one photon coming out. But at intermediate stages, I should be describing the system, including the hydrogen atom, which started with some state and it goes back to another state. So what's really different about this system relative to this hydrogen atom that just gets excited and goes back to its ground state?
Well, I mean, normally, if we have two subsystems and then we allow them to interact, we would expect them to become entangled. And if we traced out one of them, then we would get a decoherence in the other system. So the picture we have here, it's equivalent to the following thing, that we have some potentially entangling dynamics between the matter system and the infalling radiation, which may produce entanglement between them, which will have the effect that an observer looking at the matter system will think that it has decohered. But when we get to the final state condition, in effect, that entangling dynamics has become undone, and then we project onto a maximally entangled state of the two systems. So this is the kind of dynamical miracle, that those entangling interactions become undone, then we project, and in that way we can get exact unitarity. Maybe I should sum up because it's gotten kind of late. But I appreciate all the questions. I mean, look, I'm not saying that I've got the answer here. I certainly don't want to give that impression. I'm just saying that there are some features of this picture which maybe can help to guide us. I mean, I don't think anything that we've heard is exactly right, Well, look, I mean, that's what that's the quote I quoted Joe verbatim. We talk about firewalls, but we don't have any dynamics of firewalls that we understand. We talk about nonviolent non-locality, but at this point we have only very crude descriptions of how that could work. We talk about ER equals EPR and A equals RB and that kind of thing, but clearly those ideas all need further development if they're going to be the answer. So I think what may well happen is there are elements of truth in different points of view, and we have to learn how to extract a little bit of truth from different ideas and figure out how to stitch them together into some kind of consistent and compelling narrative. And I don't think that a priori this idea is necessarily far more outlandish than other things we've been talking about. Well, really. And it may even be the same, but it may provide an alternative point of view that can be very helpful. And I think in particular the idea of sort of a temporary departure from unitarity, which can allow us to have polygamous entanglement and cloning, could be an important part of the final story, but maybe that's completely wrong. But I'm just suggesting that I think it would be fruitful for these ideas to get further attention. So, thank you.